Hi everyone, this is V.Chandra Sekhar Reddy, Associate Professor in the Department of Computer Science and Engineering, ACE Engineering College. Welcome to ACE Engineering College YouTube channel and also welcome to the series of lectures on Discrete Mathematics. Now in today's session, the topics I have selected to explain you are the properties of relation, then equivalence relation, then I am going to solve some of the previous gate questions. Now the outcomes of this session are the student will be able to understand the properties of the relations. There are different properties of the relations. The student will be able to understand and categorize the properties of the relations. Next outcome is the student will understand the properties of an equivalence relation. There are some properties of the equivalence relation. The student will be able to understand what is an equivalence relation, what are the properties satisfied by this equivalence relation. These are the outcomes of this today's session. Now, properties of relation. Before I am going to explain you about the properties of the relation, let me quickly explain or revise the topics which I have explained in the previous session. Because to explain about the properties of the relation, you must have knowledge about what is the relation. So first I am explaining the relation, then we will discuss the properties of relation. So in previous session I explained that yes, I am taking two non-empty sets, A and B. A and B be two non-empty sets. The Cartesian product of A and B is denoted as A cross B. So what is A cross B? It is the set of all ordered pairs A comma B. A comma B is the ordered pair such that A is taken from the set A and B is taken from the set B. B is taken from the set B. So I am taking two non-empty sets, A and B are two non-empty sets, and the Cartesian product of A and B is denoted as A cross B and is equal to the set of all ordered pairs A comma B such that A belongs to A and B belongs to A. B belongs to B. So this is the Cartesian product. Now what is the relation means? Relation is a subset of Cartesian product. So for A cross B, there exists some subsets. Now this relation is one of the subsets. So relation is a subset of the Cartesian product. For example, if the Cartesian product is consisting of A cross B, cardinality of A cross B is equal to 6. Assume that the cardinality of A cross B is equal to 6, then there will be 2 power 6 subsets. Then there will be 2 power 6 subsets. These are all the relations. These are all the relations. If the Cartesian product is consisting of 6 elements, then there will be 2 power 6 subsets. These subsets will be the relations from set A to set B. So simply you can understand that relation is a subset of the Cartesian product. Now binary relation. Any relation which is defined from A to A itself. If the relation is defined from A to A itself, then it is called binary relations. So this is about the relation and binary relation. Now we are going to discuss about the properties of the relations. So in these properties of the relation, we are going to discuss about the reflexive relation. This is the first relation, reflexive relation. Then we are going to discuss about irreflexive relation. Then we have symmetric relation. Then we have compatibility relation, antisymmetric relation, transitive relation. These are all the properties of the relation. Now we will discuss one by one in detail. So the first one is reflexive relation. So reflexive relation means Here I am taking some binary relation, R be the binary relation, which is defined on the set A. Just now I explained what is binary relation. Binary relation is a relation which is defined from set A to A itself. So now the reflexive relation says that for all A comma A belongs to R, for all A belongs to A. That means the relation R on set A is said to be a reflexive relation if A comma A belongs to R, for all A belongs to E. That means in the set A, if you take any element small a, then there must be the mapping from A to A itself. Then there must be the mapping from A to A itself. For example, I am taking the set A is equal to 1, 2, 3. And the relation R is equal to 1, 1, 1, 2, 2, 1, 2, 2, 3, 3. So this is one relation defined on the set A. If you observe this relation, for every element in set A, there is a mapping to itself. That is, there is 1, 1, 1 is mapped to itself. There is 2, 2, 2 is mapped to itself. There is 3, 3, 3 is mapped to itself. Which means for every element in set A, there is a mapping to itself. So then R is binary, R is reflexive relation. So reflexive relation means for every element in the set A, there must be the mapping from A to A itself. Next, a relation R on set A is said to be not symmetric, not reflexive. The relation R is said to be not reflexive if A comma A does not belongs to R for some A belongs to A. If for some A belongs to A, if there is no mapping to itself, then it is called not reflexive relation. So reflexive relation means for every element in the set A, there must be the mapping from A to A itself. Not reflexive relation means for some elements, A comma A does not belongs to R. If A comma A does not belongs to R for some elements, then it is called not reflexive relation. Now we'll see the examples for this reflexive and not reflexive relations. The first, here I am taking one relation. R is the relation defined on the set A is equal to 1, 2, 3, 4. So here R is a binary relation which is defined on the set A. Now R is consisting of all the ordered pairs 1, 1, 1, 2, 2, 1, 2, 2, 3, 3, 4, 4. Now according to the definition of reflexive relation, if there is A comma A belongs to R, if A comma A belongs to R, for all A belongs to A, then it is reflexive relation. Then it is reflexive relation. Now if you observe this relation, there is 1, 1, there is 2, 2, there is 3, 3, there is 4, 4. Which means for every element in the set A, there is a mapping to itself. Therefore, this is reflexive relation. Let us see one more example. Now I am taking the general relation is less than or equal to. I am taking some relation which is defined on set of all real numbers. The relation is less than or equal to. Is less than or equal to. This is also written as like this. The relation which is defined is less than or equal to on set of all real numbers. Set of all real numbers. If you observe this relation, this is reflexive relation, because if you take any real number, then that real number will be less than itself or equal to it. That is, 1 is equal to 1. The relation is either less or equal. The relation is either less or equal. So if you take the relation less than or equal to, then it is reflexive relation, because the relation is either less or equal. When we consider equal, 1 is equal to 1. Take any real number, not only 1, take the positive real numbers, take the negative real numbers, and any real number, that real number is equal to itself. Therefore, the relation less than or equal to is a reflexive relation. Similarly, the relation is greater than or equal to, which is nothing but like this, greater than or equal to. It can be either greater or it can be equal. It can be either greater or it can be equal. So, the relation greater than or equal to on set of real numbers is also a reflexive relation because every real number is equal to itself. So, the relation less than or equal to and greater than or equal to on set of all real numbers are reflexive relations. Now, I will see one more example. The relation is less than. The relation is less than. If we take the relation is less than on set of all real numbers, set of all real numbers. If you take the relation is less than, only less than, there is no equal. So if you take less than, then this is not a reflexive relation, because if you take any real number, it will be equal to itself, but it will not be less than itself. Similarly, the relation is greater than, is greater than. This is also not a reflexive relation. That is also not a reflexive relation. That means is less than and is greater than on set of all real numbers are not reflexive relations, because every real number will be equal to itself. It will never be less than or it will never be greater than itself. So this is about the reflexive and not reflexive relations. Now we'll see some important points based on the reflexive and irreflexive relation. In the previous session, I explained the matrix representation and diagram representation of the relation. That means if you take any relation, this will be represented in two ways. One is matrix representation, another one is digraph representation. Digraph representation is nothing but directed graph representation. So when we are writing the matrix representation of the relation, it is denoted as MR. MR is the matrix representation of the relation. For example, if you take a relation R from set A to B, so the cardinality of A is N and the cardinality of B is M. If R is the relation from set A to set B, set A is consisting of N elements and set B is consisting of M elements, then the matrix representation is of N cross M matrix, where N denotes the number of elements in set A and M denotes the number of elements in set B. And the elements in this matrix are zeros and ones. If there is a relation from 1 to 1, then it will be indicated with 0. If there is no relation, then it is indicated with 1. If there is a relation from 1 to 1, it is indicated with 1. If there is no relation, it is indicated with 0. So, if 1 comma 1 belongs to R, then it is indicated with 1. If 1 comma 1 does not belongs to R, then it is indicated with 0. So, the matrix representation of the relation will be consisting of binary numbers. So, binary numbers means either 0 or 1. The order of the matrix is N cross M, where N is the number of elements in set A and M is the number of elements in set B. So this is the matrix representation of the relation. Now I'll see the first point. So the first point says, if R is a reflexive relation, then all the principal diagonal elements, are main diagonal elements of the matrix representation are equal to 0. If you take the reflexive relation, then if you take the matrix representation of the reflexive relation, that matrix will be consisting of only ones in the main diagonal. Main diagonal means if you take the matrix representation like this, which is equal to Ai comma j, where N cross M, if Ai comma j, the elements Ai comma j for I is equal to j are called main diagonal elements. Main diagonal elements. What are the main diagonal elements means? The elements a, I, comma j where I is equal to j are called main diagonal elements. That means when we take the matrix representation, these elements are called main diagonal elements because 1, 1. This represents 1, 1. This represents 2, 2. Like this is represents n, n. This is called main diagonal. So the reflexive relation means there is a mapping from A to A itself. That means A, A belongs to R. A belongs to R means all the principal diagonal elements are equal to 1. So if R is the reflexive relation, then all the principal diagonal elements are equal to 1. This is the first point you need to remember. Coming to the second point. If R is the reflexive relation, then the diagram representation of reflexive relation will be consisting of loops at every vertex. So this is the reflexive relation. This reflexive relation, if you take the matrix diagram representation of the reflexive relation, then the diagram representation of the reflexive relation means the diagram will be consisting of vertices and edges. Edges are nothing but ordered pairs. Vertices are nothing but the number of elements in the set A. Every element in the set A will be represented with one dot, that is called vertex, and every ordered pair will be represented with an arrow. That arrow is called edge. So if R is the reflexive relation, then the diagram representation of the reflexive relation will be consisting of all the loops at every vertex. Since A, A belongs to R. A belongs to R is nothing but there is a edge from A to A itself. There is a edge from A to A itself. If there is a edge from A to A itself, then the vertex A will be having loop. So the second point says the diagram representation of a reflexive relation will be consisting of loops at every vertex. These two are the very important point you need to remember. Now the next property is irreflexive relation. So far we have seen reflexive relation. Reflexive relation means A, belongs to R. A belongs to R for all A belongs to E. This is called reflexive relation. Not reflexive. Not reflexive means A, does not belongs to R for some A belongs to E. For some A belongs to E. So this is reflexive relation. This is the not reflexive relation. So reflexive relation means for all A belongs to A, A belongs to R. Not reflexive relation, for some A belongs to A, A does not belongs to R. Now we'll see what is irreflexive relation. So the irreflexive relation says that A, does not belongs to R for all A belongs to E. A, does not belongs to R for all A belongs to E. If A, belongs to R for all A belongs to A, reflexive. If A, does not belongs to R for some elements in set A, then that is not reflexive. Irreflexive means for every element in set A, A, does not belongs to R, which means there should not be any mapping from the element A to A itself for any element in the set A. Then it is called irreflexive relation. This is the main difference between reflexive, not reflexive, and irreflexive. Please remember, not reflexive is not same as irreflexive. Both of them are two different relations. Not reflexive means for some elements A, does not belongs to A. When it comes to the irreflexive, A, does not belongs to R for every element in the set A. So this is the main difference between reflexive, irreflexive, and not reflexive. Now we'll see some examples for this irreflexive relation. So the relation, here I have taken some binary relation defined on the set A is equal to 1, 2, 3, 5. If you look at this set and this relation, this is the relation defined on this set. If you observe this relation, there is no 1, 1. There is no 1 comma 1. 1 comma 1 does not belongs to R. Similarly, 2 comma 2 does not belongs to R. Next, 3 comma 3 does not belongs to R. Next, 4 comma 4 does not belongs to R. And 5 comma 5 does not belongs to R. Does not belongs to. That is, A comma A does not belongs to R for all small a belongs to capital A. So if you observe this relation is not consisting of 1 comma 1. It doesn't have 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, 5 comma 5. That means for every element in this set A, there is no mapping to itself in this relation R. That's why this relation R is irreflexive relation. So that is the example for the irreflexive relation. Now I'll see one more example. The next example is less than. I am taking the relation is less than on set of all real numbers. Here capital R is nothing but set of all real numbers. R is set of all real numbers. If you take set of all real numbers and the relation R, take any element in the real number system. That is, for all A belongs to real number system R, A will never be less than A. A will never be less than A, which means A comma A does not belongs to R. A comma A does not belongs to R, which means every real number is equal to itself, but it will never be less than itself and it never be greater than itself. Therefore, the relations is less than and is greater than are irreflexive relations on set of all real numbers. Now look at this. There are some note points which are depending on this irreflexive relation. Just now we have discussed about the matrix representation and diagram representation of the reflexive relation. So if you take the irreflexive relation, R is the irreflexive relation on set of all real numbers, then the matrix representation of this irreflexive relation will be having zeros and ones, especially the main diagonal will be consisting of zeros. That means all the main diagonal elements of the matrix representation of the reflexive relation are zero, because A comma A does not belongs to R. A comma A does not belongs to R. A comma A does not belongs to R means if A comma A does not belongs to R, then it is indicated with 0. Then it is indicated with 0. That means all the principal diagonal or main diagonal elements of irreflexive relation are zeros. The next point is look at the next point. Similarly, if you take the diagram representation of the irreflexive relation, it will never consist of loops. It will never consist of loops. So when we take an irreflexive relation, and if you take the diagram representation of it, that diagram representation will not be having any loops. These are the two important points related to the irreflexive relation. The matrix representation of the irreflexive relation will be consisting of all zeros in the principal diagonal. Similarly, the second point says the matrix representation of the irreflexive relation will be the diagram representation of the irreflexive relation will be consisting of no loops at any vertex. Now the next property is symmetric property. The next property is symmetric property, symmetric relation. Now what is the definition of symmetric relation? A comma B, B comma A belongs to R whenever A comma B belongs to R. For example, if there is A comma B in the relation R, then B comma A must be there. If B comma A is also there, then such type of relation is called symmetric relation. Symmetric relation says if A comma B belongs to R, if A comma B belongs to R, then B comma A belongs to R. Then B comma A belongs to R. This is the conditional statement. This is the conditional statement like P conditional Q. So here what is P? The statement P is A comma B belongs to R. The conditional Q is B comma A belongs to R. B comma A belongs to R. So this is the conditional statement P conditional Q, where P is A comma B belongs to R and Q is B comma A belongs to R. So whenever B comma A belongs to R, if A comma B belongs to R, then that relation is called symmetric relation. Now I'll see the examples for the symmetric relations. If, for example, if A comma B belongs to R, B comma A does not belongs to R, then it is not a symmetric relation. For example, if A comma B belongs to R, A comma B belongs to R, but B comma A does not belongs to R. B comma A does not belongs to R. Then such type of relation is called not symmetric relation. Such type of relation is called not symmetric relation. This is about symmetric relation and not symmetric relation. We will see the examples for symmetric and non-symmetric. This is the definition of not symmetric relation. Whenever A comma B belongs to R, if B comma A does not belongs to R, then the relation R is said to be not symmetric relation. This not symmetric relation is also called asymmetric relation. Asymmetric relation is nothing but not symmetric relation. When we say that the relation is asymmetric or not symmetric, A comma B present in R, but B comma A does not present in R. If A comma B belongs to R, but B comma A does not belongs to R, then it is not symmetric. For example, if A comma B belongs to R and B comma A is also belongs to R, then it is called symmetric relation. Now I'll see the examples for this. Now I am taking some binary relation which is defined on the set A is equal to 1, 2, 3, 4. I am taking 4 elements in the set A and I have taken some ordered pairs in the relation R. That is the binary relation which is defined on the set A. Now I am going to verify whether this is symmetric relation or not. So the property for the symmetric relation is if A comma B belongs to R, if A comma B belongs to R, then B comma A belongs to R. Then B comma A belongs to R. Now if you observe this, this is of the form A comma B. So 1 comma 2 is of the form A comma B. And there is B comma A. There is B comma A. So 1 comma 2 is there, 2 comma 1 is there. Similarly, 1 comma 3 is there. This is like A comma B. 1 comma 3 is there. 3 comma 1 is also there. This is B comma A. Next, this is like A comma B. 2 comma 4. B comma A is 4 comma 2. That is, for all ordered pairs, A comma B belongs to R, B comma A is also belongs to R. B comma A is also belongs to R. Therefore, the given relation is symmetric relation. The given relation is symmetric because 1 comma 2, 2 comma 1. 1 comma 3, 3 comma 1. 2 comma 4, 4 comma 2. For every ordered pair A comma B, there is B comma A also. Therefore, the relation R is symmetric relation on the set A is equal to 1 comma 2 comma 3. Next, I am taking some other example. R is equal to 1 comma 2, 1 comma 4, 2 comma 1, 2 comma 4, 3 comma 1, 4 comma 2. On the set A is equal to 1 comma 2 comma 3 comma 4. So now look at this. There is 1 comma 2. Comma 1 is also there. There is 1 comma 4. But 4 comma 1 does not belongs to R. Here in the given relation there is 1 comma 4. But 4 comma 1 does not belongs to R. Therefore, this relation is not symmetric relation. That means this is asymmetric relation. So whatever relation I have taken in second example, That is the symmetric relation. The reason is 1, 4 is present in the relation R, but 2, 1 does not present in the relation R. Therefore, this is not a reflexive relation. Not a reflexive relation means asymmetric relation. That is called asymmetric relation. Now we'll take some general relations. Is less than or equal to, is less than or equal to, and is greater than or equal to on set of all real numbers. If you take is less than or equal to and is greater than or equal to, both of them are not symmetric relations. The reason is that if A is less than or equal to B, then B will never be less than or equal to A. B will never be less than or equal to A. Similarly, if A is greater than or equal to B, then B will never be greater than or equal to A. B will never be greater than or equal to A. So, the relation is less than or equal to and is greater than or equal to on set of all real numbers are not symmetric relations. Now, the next property is compatibility relation. So, the compatibility relation says that if the binary relation on set A satisfies reflexive and symmetric property. If the binary relation R on the set A is satisfying reflexive property and symmetric property, then we say that is compatibility relation. So compatibility relation means which is both reflexive and symmetric. Now we'll see one example. So I am taking some binary relation which is defined on the set A is equal to 1, 2, 3, 4. Now first I am going to verify whether this relation is reflexive relation or not. Then I am going to verify whether this relation is symmetric or not. If it is both reflexive and symmetric, then it is called compatibility relation. Now first, there is 1, 1, there is 2, 2, there is 3, 3, there is 4, 4. That means for every element in the set A, there is 1, 1. 1, 1 belongs to R, 2, 2 belongs to R, 3, 3 belongs to R, and 4, 4 belongs to R. 4, 4 belongs to R. That is, for every element in set A, there is a mapping to itself. Therefore, this relation is reflexive. Now, symmetric relation. There is A, B, there is B, A. 1, 2, 2, 1. 2, 4, 4, 2. That means, for every ordered pair which is of the form A, B, B, A is also present. A, B, A is also present. That is, 1, 2 belongs to R implies 2, 1 is also belongs to R. Next, 2, 4 belongs to R implies 4, 2 is also belongs to R. 4, 2 is also belongs to R. Therefore, this is belongs to. So, 1, 1 is there, 2, 2 is there, 3, 3 is there, 4, 4 is there. Therefore, the given relation is reflexive relation. 1, 2 belongs to R, 2, 1 is also belongs to R. 2, 4 belongs to R, 4, 2 is also belongs to R. Therefore, it is symmetric relation. So, this relation is satisfying reflexive property and symmetric property. Therefore, it is compatibility relation. The next example. Is less than or equal to. If you take the relation is less than or equal to. Just now we have seen is less than or equal to is the only reflexive relation but not a symmetric relation. Therefore, is less than or equal to is not a compatibility relation because it is not satisfying symmetric property. Similarly, is greater than or equal to. This is also not a compatibility relation because it satisfies only reflexive property but it will never satisfy symmetric property. Therefore, it is not a compatibility relation. So, both less than or equal to and less than or greater than or equal to are not compatibility relations because both of them are not satisfying symmetric property. The next example is this. Or is the relation defined on the set A is equal to 1, 2, 3, 4. If you look at this, there is 1, 1, there is 2, 2, there is 3, 3, there is 4, 4. Therefore, the relation is satisfying reflexive property. 1, 4 is there, but 4, 1 does not belong to R. Here, 1, 4 belongs to R, but 4, 1 does not belong to R. 4, 1 does not belong to R. Therefore, this relation is not satisfying symmetric property. It is satisfying only reflexive property, but this relation is not satisfying symmetric property. Therefore, this relation is not a compatibility relation. So, compatibility relation means any relation which satisfies reflexive property and symmetric property. These are the examples for the compatibility relations. Now, next property is antisymmetric. This is the next property of the relation, antisymmetric. We have seen symmetric property and not symmetric. Symmetric means if A, B belongs to R, B, A must be belongs to R. Not symmetric means if A, B belongs to R, but B, A does not belongs to R. That is not symmetric. Not symmetric relation is also called asymmetric relation. The next one is antisymmetric relation. Now let us see what is antisymmetric relation. The antisymmetric relation says that whenever A, B belongs to R, B, A belongs to R, then A must be equal to B. So the condition is if A, B belongs to R and B, A belongs to R, then A is equal to B. That is the property, that is the condition for the antisymmetric relation. If there is an ordered pair A, B and B, A, then A must be equal to B. Then we say that the given relation is antisymmetric relation. Otherwise, that is if A is not equal to B, then it is not an antisymmetric relation. So, whenever A, B belongs to R, B, A belongs to R, A must be equal to B. Then we say that that relation is antisymmetric relation. Otherwise, it is not antisymmetric relation. Now, if you look at a relation, is less than or equal to. Is less than or equal to. Is less than or equal to means this one. Is less than or equal to. For example, if A is less than or equal to B and B is less than or equal to A, then A must be equal to B. Then A must be equal to B. So if there is an ordered pair A, B and B, A, then it will be possible only when A and B are equal. If A is less than or equal to B and B is less than or equal to A, then A and B must be equal. So the relation is less than or equal to is antisymmetric relation. Similarly, the relation is greater than or equal to. If A is greater than or equal to B and B is greater than or equal to A, then A must be equal to B. A must be equal to B. So if A is greater than or equal to B and B is greater than or equal to A, then both A and B must be equal to each other. So the relation is less than or equal to and is greater than or equal to, both of them are antisymmetric relations. Next example, divisibility. The relation divisibility on set of all positive integers, on set of all positive integers defined by A divides B, which is denoted as like this. So this is the symbol which we use for divisibility. This is symbol which we use for divisibility. So here I am taking divisibility relation on set of all positive integers. On set of all positive integers. Positive integers means 1, 2, 3 and so on like that. And this relation is defined by A divides B. Symbolically it is denoted like this. A divides B is an antisymmetric relation. The reason is if A divides B and B divides A, then A and B must be equal to B. A and B must be equal to each other. So if A is dividing B and B is dividing A, then that is possible only when both the numbers are equal to each other. So the relation divisibility on set of all positive integers is antisymmetric relation. Antisymmetric relation. Next, subset. If you take the relation subset, so here I am taking some set S. The subset of S is denoted like this. Subset. So this is the subset relation. So the relation subset defined on power set of A. So if you take some set A, then the power set of A is denoted P of A. This is set A. The power set of this is denoted as P of A. So what is P of A means? The set of all subsets of A. This is the given set. For this set, there exist some subsets. If you take the set of all those subsets, then you will be getting P of A. P of A is a power set of A. P of A is a power set of A. Is an antisymmetric relation. The reason is, if A is subset of B and B is subset of A, then A and B must be equal. A and B must be equal. So in the previous lecture, in one of the previous lectures, I explained about the equal sets. The definition of equal sets are, if A is subset of B and B is subset of A, then A and B are equal to each other. So for any two subsets, if A is a subset of B and B is a subset of A, then the two subsets A and B are equal to each other. Therefore, the subset defined on power set of A is an antisymmetric relation. Is an antisymmetric relation. So this subset which is defined on power set of A satisfies antisymmetric property. Therefore, this is antisymmetric relation. This is the reason why it is antisymmetric relation. Now I'll say the next property, that is transitive property. The next property of the relation is transitive property. You will see what is transitive property. So here, whenever A comma B belongs to R, B comma C belongs to R, then A comma C must be belongs to R. So if there is A comma B belongs to R, B comma C belongs to R, then A comma C must and should belongs to R. This is the symmetric property. If there is an ordered pair A comma B and B comma C, then there must be the ordered pair A comma C in the relation R. Then we say that that relation is transitive relation. Otherwise, we say that the relation R is not transitive. When the relation R is not transitive, A comma B is present in R, B comma C is present on R, but A comma C does not present in R. A comma C does not belongs to R. Then we say that the relation R is not transitive relation. So this is about the transitive relation. Now we'll see the examples for the transitive relation. So here, this is the definition of transitive relation, and this is the definition of not transitive relation. Next examples, same example, is less than or equal to, is less than or equal to. So for example, I am taking two elements, A is less than or equal to B and B is less than or equal to C. Then A must be less than or equal to C. Take any three real numbers such that A is less than or equal to B and B is less than or equal to C, then A must be less than or equal to C. For example, I am taking three real numbers. 2 is less than or equal to 3 and 3 is less than or equal to 4. This implies 2 is less than or equal to 4. Not only these three real numbers, take any three real numbers A, B, C. If A is less than or equal to B, B is less than or equal to C, then A is less than or equal to C. That we have seen with this example. Similarly, the relation greater than or equal to, if you take the relation greater than or equal to, if A is greater than or equal to B and B is greater than or equal to C, then A must be greater than or equal to C. Then A must be greater than or equal to C. For any three real numbers, if A is greater than or equal to B and B is greater than or equal to C, then A must be greater than or equal to C. That means the relations is less than or equal to, is greater than or equal to are transitive relations on set of all real numbers. On set of all real numbers. Next example is, I am taking the divisibility relation. Divisibility relation, A divides B. A divides B. And it is denoted like this. On set of all positive integers. On set of all positive indices. If you take the divisibility relation, this divisibility relation is also transitive relation. The reason is, if A divides B, B divides C, then A must and should divide C. For example, 2 divides 4 and 4 divides 8. This implies 2 divides 8. So this is like A divides B. This is like B divides C. This is A divides C. So for any three positive integers A, B, C, if A divides B, B divides C, then A must and should divide C. This is the divisibility relation. The relation divisibility relation is transitive relation. Similarly, the relation subset defined on power set of A, which is denoted as P of A. A is transitive relation because if A is a subset of B, B is a subset of C, then A is a subset of C. For any three sets, if A is subset of B, B is subset of C, then A must be subset of C. Therefore, the relation subset defined on power set is also transitive relations. So this is about the transitive relations. So these are all the properties of the relations. We have seen reflexive relation, not reflexive, irreflexive, symmetric, not symmetric, antisymmetric, transitive, and not transitive. These are all the properties of the relations. Now we'll take some example. We'll discuss some examples. I am taking the set A is equal to 1, 2, 3, 4, and I am taking some relations. We will see whether these relations are, whether they are reflexive, symmetric, or transitive or not. The first relation is this. R1 is equal to 1, 2, 2, 1, 1, 3, 3, 1. Is it reflexive? No, this is not a reflexive because A, does not belong to R. If it is not reflexive, then what type of reflexivity is? Irreflexive relation. This is irreflexive relation. So why it is irreflexive? Because for all A belongs to A, A, does not belongs to R. 1, 1 is not there, 2, 2 is not there, 3, 3 is not there, 4, 4 is also not there. Therefore, 4 is not there, only 1, 2, 3. 1, 1, 2, 2, 3, 3 does not belongs to A relation R1. Therefore, it is not a reflex. That is irreflexive. For every element, there is no mapping to itself. That is one thing. The other one is it symmetric? Yes, 1, 2 is there, 2, 1 is there. 1, 3 is there, 3, 1 is there. Therefore, this is symmetric relation. Whatever relation we have taken, R1 is a symmetric relation. Now, is it transitive relation? It's like A, B, and this is B, C, A, C, 1, 1. 1, 1 does not belong to R. Therefore, it is not transitive. This is not a transitive relation. So, The relation R1 is only symmetric and irreflexive and not symmetric. So now I'll see the next example. So R2 is equal to 1, 1, 2, 1, 2, 3, 3, 2, 3. So if you observe this relation, there is 1, 1, there is 2, 2, there is 3, 3. Therefore, this is reflexive relation. For all elements in set A, there is a mapping to itself. Therefore, this is reflexive. Next, is it symmetric? 2, 3 is there, but 3, 2 does not belong to R. Only 2, 3 is there, but 3, 2 does not belong to R. Therefore, it is not symmetric. This is not symmetric relation. Next, this is not symmetric relation. Next one is transitive relation. This is like A, B. A, B is there. This is like B, C. So A, C. A, C means 2, 3. Yes, 2, 3 is there. So here 2, 2 belongs to R and 2, 3 belongs to R. This implies 2, 3 belongs to R. It's like A, B, B, C. A, C is 2, 3 belongs to R. Therefore, this relation is transitive relation. This one is transitive relation. So, the second one is R2 is reflexive, it's not symmetric and transitive. The next one is R3 is equal to 1, 1, 2, 2, 3, 3. Is it reflexive? Yes, 1, 1 is there, 2, 2 is there, 3, 3 is there. This is the reflexive relation. Now, is it symmetric? Yes, this is symmetric. The reason is, if A, B belongs to R, if A, B belongs to R, then only you need to verify B, A belongs to R or not. If A, B belongs to R is there, then you need to verify whether B, A belongs to R or not. If A, B is not there, then it is obviously symmetric relation. So R3 is reflexive relation and symmetric relation. Now R4, 1, 1 is there, 2, 2 is there, 3, 3 is there. Therefore, it is reflexive relation. R4 is reflexive. Next, 2, 3 is there, 3, 2 is there. So, it is symmetric. Next, this is like A, B, B, C. So A, C means 3, 2. Yes, it is there. Next, it's like A, B. This is B, C. A, C means 2, 3. So therefore, this is transitive relation also. So whatever relation is given in R4, that is reflexive relation, symmetric relation, transitive relation. Now the last one is look at this 2, 3. This is not a reflexive. Not reflexive means irreflexive relation because 1, 1 is not there. This is not 2, 3, 3, 2. This is 2, 1, not 2, 4. So 2, 3 is there, 3, 2 is there, 2, 1 is there, 1, 2 does not belong to R. Therefore, this is not a symmetric relation. This is irreflexive relation. Now, what about transitive relation? This is like A, B. This is like B, C. A, C means 2, 2. 2, 2 does not belong to R. 2, 2 does not belong to R. Therefore, R5 is irreflexive relation, not symmetric and not transitive. So this is how we need to verify whether the given relation is satisfying, whether the given relation is reflexive or not, transitive or not, symmetric or not. Then the next one is equivalence relation. This is very important for the examination point of view. You will definitely expect, you can expect one question from this equivalence relation. If the relation binary relation R satisfies some properties, then we say that the relation R is equivalence relation. Now we'll see what are all the properties the binary relation should satisfy to become the equivalence relation. So the first one, so the relation R must be reflexive. So the relation R must be reflexive. This is the first point. R must be reflexive. The second one is R must be symmetric, and the third one is R must be transitive. So if the binary relation R satisfies reflexive property, symmetric property, and transitive property, then we say that R is the equivalence relation defined on the set E. So reflexive property, symmetric property, and transitive property. And now let's see some examples. So already we have seen these examples. E is less than or equal to. It is only reflexive and transitive. It's not a symmetric. It's not a symmetric. Therefore, E is less than or equal to is not a equivalence relation. The reason is they are not symmetric. They are not symmetric. Similarly, the relation E is greater than or equal to. E is greater than or equal to is not a equivalence relation because E is greater than or equal to will not satisfy symmetric property. So the relations E is less than or equal to and E is greater than or equal to on set of all real numbers are not equivalence relations. The next one. The next example is subset. Subset defined on the power set. So subset satisfies reflexive relation because if you take any set, then it is a subset of itself. A is a subset of itself. In previous session when I was explaining about the sets, I have clearly explained this. Every set is a subset of itself. Take any set, it will be the subset of itself. So A is a subset of itself, that is reflexive. So the relation subset satisfies reflexive relation, reflexive property. The second one, what is second one? If A is subset of B, if A is subset of B, then B will not be a subset of A. B will not be a subset of A. That you can see with this example. I am taking A is equal to 1, 2. B is equal to 1, 2, 3. If you take these two sets, here A is a subset of B because all the elements which are there in A are the elements of B. Therefore, A is subset of B. But B is not a subset of A. B is not a subset of A. So this subset relation is not satisfying symmetric property. Therefore, this relation is not an equivalence relation. So the relation subset satisfies only reflexive property. It is not going to satisfy symmetric property. Then you need not to verify the transitive property. If the relation is not satisfying any one of the properties, then it will not be a equivalence relation. Now the third example. So this is the relation R is equal to 1, 1, 1, 2, 2, 1, 2, 2, 3, 4, 4, 3, 3, 3, 4, 4 defined on the set A. So A is equal to 1, 2, 3, 4. If you observe this, there is 1, 1. There is 2, 2. There is 3, 3. There is 4, 4. Therefore, this relation is satisfying reflexive property. This is reflexive. So the relation is reflexive. Now we'll verify symmetric. 1, 2 is there, 2, 1 is there, 3, 4 is there, 4, 3 is there. Therefore, the relation R is symmetric. The relation R is symmetric. Next I am going to verify the transitive property. Here, 3 comma 4 is there and 4 comma 3 is there. It's like A comma B and B comma C. Then what is A comma C? 3 comma 3. Yes, 3 comma 3 belongs to R. 3 comma 3 belongs to R. Similarly, 1 comma 2 is there, 2 comma 1 is there. This implies A comma C. 1 comma 1 is also belongs to R. So, like this, if you take any two ordered pairs, A comma B belongs to R and B comma C belongs to R, then A comma C is also belongs to R. Then A comma C is also belongs to R. Therefore, the relation R satisfies transitive property also. The relation R satisfies transitive property also. So, the relation R is satisfying reflexive property, symmetric property and transitive property. Therefore, this is an equivalence relation. This is an equivalence relation. Now, we will see some problems. So, here I am taking some problem. So, this is set A and this is the relation. Be a relation from relation on A, verify that R is the equivalence relation on R. They have given some relation on the set A, then they are asking us to verify whether it is equivalence relation or not. The first one is reflexive. First I am going to verify whether this is satisfying reflexive property or not. So here first one. Here 1 comma 1 is there, 2 comma 2 is there, yes 1 comma 1 is there, 2 comma 2 is there, 3 comma 3 is there, next 4 comma 4 is also there. So 1 comma 1 is there, 2 comma 2 is there, 3 comma 3 is there, 4 comma 4 is there. Therefore, it is reflexive. The given relation is satisfying reflexive property. So, the given relation is satisfying reflexive property. Now, the second one. Here 1 comma 2 belongs to R. This implies 2 comma 1 is also belongs to R. Similarly, 3 comma 4 belongs to R. 3 comma 4 belongs to R. This implies 4 comma 3 is also belongs to R. 4 comma 3 is also belongs to R. That means for every ordered pair A comma B, there is B comma A also. Therefore, it is satisfying symmetric property also. The given relation is symmetric relation also. Now, I am going to verify the transitive property. So, here 1 comma 2 is there, next 2 comma 1 is there. This implies 1 comma 1 is also belongs to R. Similarly, 3 comma 4 is there, 4 comma 3 is there. This implies 3 comma 3 is also belongs to R. 3 comma 3 is also belongs to R. That means for every ordered pair A comma B and B comma C, there is A comma C also. Therefore, it is satisfying transitive relation or transitive property also. So, the relation R is satisfying reflexive property, symmetric property and transitive property. Therefore, the given relation is an equivalence relation. Whatever relation they have given, that is an equivalence relation. Now, I will see one more problem. This problem is very, very important for the external examination point of view. This is the frequently asked question. If you look at the previous question paper, in every question paper, this question will be there. So, for any fixed integer n is greater than 1, prove that the relation congruent modulo n. They have given some relation. Congruent modulo n is an equivalence relation on set of all integers. On set of all integers. This is the problem. So they have given some relation that is congruent modulo n on set of all integers. Now let's see what is congruent modulo n relation. So what is the congruent modulo n relation? So this is the congruent modulo n relation. So the congruent modulo n relation says if A minus B is a multiple of n, if A minus B is a multiple of n, then we say that A is congruent to B mod n. Symbolically it is written like this. A is congruent to B mod n. So A is congruent to B mod n when A minus B is multiple of n. If A minus B is multiple of n, then it is written like this. A minus B is equal to Kn for some K value. So this is about the congruent modulo n relation. A is congruent to B mod n if A minus B is a multiple of n. Now that is the given relation. A is congruent to B mod n. Now we are going to check whether this is equivalence relation or not. To check this, you need to verify reflexive property, symmetric property, and transitive property. So now we'll see whether it is satisfying the reflexive property or not. So the reflexive property, if I take any integer A, for any integer A minus A is a multiple of n. If I take any integer, then A minus A is a multiple of n. A minus A is equal to 0. Here A minus A is equal to 0. 0 can be written 0 into n. 0 can be written 0 into n. That means for any integer A minus A is multiple of n. Therefore, A is congruent to A mod n. A is congruent to A mod n. That is, the relation R satisfying reflexive property, which means the congruent modulo n is a reflexive relation. Now let's see the second property. The second property is symmetric property. So to verify symmetric property, I am taking two elements, A comma A, B belongs to Z, and if A is congruent to B mod n, if A is congruent to B mod n, I am going to verify whether B is congruent to A or not. So A is congruent to B mod n is nothing but A minus B is a multiple of n. So A minus B is a multiple of n. If A minus B is a multiple of n, then B minus A is also multiple of n. So B minus A is multiple of n is nothing but B is congruent to A mod n. That is a simple mathematical logic. If A minus B is a multiple of n, then B minus A will be multiple of n. So here A or B, if there is a relation, if there is ordered pair A comma B, then B comma A is also present in the relation R. That means the given relation satisfies symmetric property. So this is the symmetric property. Now let's see the transitive property. A comma B comma C belongs to Z, and A or B and B or C, which means if A is congruent to B mod n, B is congruent to C mod n, then you need to prove A is congruent to C mod n. That means A is congruent B mod n and B is congruent C mod n. So A is congruent B mod n is nothing but A minus B is a multiple of n. B is congruent C mod n is nothing but B minus C is a multiple of n. Now I am going to add them. A minus B plus B minus C minus B plus B cancel. Then you will be getting A minus C is a multiple of n. A minus C is a multiple of n is nothing but A is congruent to C mod n. A is congruent to C mod n. Therefore, the given relation satisfies transitive property also. So the congruent modulo n relation satisfying reflexive property, symmetric property, and transitive property. Therefore, the congruent modulo n is an equivalence relation. Congruent modulo n is equivalent relation. This is about this problem. Now equivalence class. So this already we have seen equivalence relation. Equivalence relation means a relation which is satisfying reflexive property, symmetric property, and transitive property. Then we are going to see what is equivalence class. this equivalence class is defined for the elements. The equivalence class is defined for the elements in the set A. For example, if R is the equivalence relation defined on the set A, then for every element in set A, we can define the equivalence class. So this equivalence class is defined for the elements in the set A. So that's why I am taking R is an equivalence relation. R is in equivalence relation on the set A. R is in equivalence relation on the set A. If R is equivalence relation, then only we can define the equivalence class for the elements of A. So R be the equivalence relation on A, and I am taking one element in the set A, then I am going to define what is the equivalence class of A. So the equivalence class of A is denoted by like this, or R of A or A bar. The equivalence class of any element is denoted like this and is defined as the set of all elements X of A are related to A by the relation R is called equivalence class of A. So symbolically it is denoted like this. Look at this, you can easily understand this. So the equivalence class of the element A is equal to the set of all elements X that X must be related to A. X must be related to A. So you need to take all the X elements which are mapped to A, then you will be getting the equivalence class of A. So the equivalence class of A is nothing but the set of all elements of A which are mapped to A, Now we'll see one example, then you can easily understand it. So here I am taking some equivalence relation. R is the equivalence relation because it is satisfying reflexive property, symmetric property, and transitive property. Now I am going to define the equivalence class of every element. If you look at the equivalence class of 1, so when we are finding the equivalence class of A1, you need to take all the elements which are mapped to 1. So here 1 is mapped to 1. Next 2 is mapped to 1. Next 3 is mapped to 1. So these are all X. What are the X values? X is equal to 1, X is equal to 2, X equal to 3. So 1, 2, 3 are mapped to 1. 1, 2, 3 are mapped to 1. The equivalence class of 1 are nothing but the set of all elements which are mapped to 1. 1 is mapped to 1, 2 is mapped to 1, 3 is also mapped to 1. Now this is the equivalence class of 2. 1 is mapped to 2, 2 is mapped to 2. So the equivalence class of 2 is only 1, 2. The equivalence class of 3, 1 is mapped to 3, next 3 is also mapped to 3, 1, 3. Equivalence class of 4, only 4 is mapped to 4. Only 4 is mapped to 4. Therefore, the equivalence class of 4 is only the element 4. This is about the equivalence class. So the equivalence class is defined for the elements in the set A when R is the equivalence relation defined on the set A. Now we'll see the partition of a set. So if any set is given, then how we are going to partition it. So let A be a non-empty set. A be a non-empty set. And suppose there exist non-empty subsets. These are all the non-empty subsets of A. I have taken some non-empty set A. Then I am going to take all the non-empty subsets of A. These are all the subsets of A. If these subsets satisfies two conditions, then we say that these are the partitions of set A. The two conditions. Condition number 1, A must be union of all the subsets. So whatever subsets we are taking, if you take the union of them, you have to get the given set. That is the condition number 1. Condition number 2 says, take any two sets, there should not be any common elements. If there are no common elements between any two sets, then we say that they are disjoint sets. If AI intersection AJ is equal to pi, which means that AI and AJ are disjoint sets. If any subset, if the subsets A1, A2 and so on AK satisfies condition number 1, condition number 2. Condition number 1 is the union of all the subsets is equal to given set. That is condition number 1. Condition number 2 is if you take any two subsets, there should not be any common elements. So if the subset satisfies these two conditions, then we say that P is the partition constituted by these subsets. P is the partition constituted by these subsets, and these subsets are called cells or blocks. Cells are blocks of the partition. So every set can be made as a partition set. If you take any set A, then you can find out the partition of that set. To find out the partition of this set, you need to find out the subsets. When you are finding the subsets, you have to make sure that these subsets satisfy these two properties. Property number 1, if you take the union of subsets, then you have to get the given set. If you take any two subsets, there should not be any common elements. Now I will take one example. So I am taking some set A. So here this is one subset, A1, A2, A3. These are three different subsets. If you look at these three different subsets, if you take the union of them, then you are going to get the given set. So here A1 union, A2 union, A3 is equal to 1, 2, 3, 4, 5, which is nothing but A. The union of all the subsets is equal to given set. And if you look at any two sets, there are no common elements. Every two sets are not having any common elements. Therefore, these subsets are satisfying the conditions of the partition of a set. Therefore, this is one partition. Similarly, there exist other partitions also. This is some other partition. This is A1, A2, A3. So if you union them, you are getting the given set. If you take the intersection of any two sets, there are no common elements. So this is other partition. P2 is equal to A1, A2, A3. This is the partition of A. Now I'll see one example. Here they have given some relation, and they are asking us to find the partition induced. The partition induced by this relation R. Determine the partition induced by the relation R. So first I am finding the equivalence class of every element. As this is equivalence relation, I am finding the equivalence class of every element. The equivalence class of 1 is mapped to 1, next 2 is mapped to 1, next 3 is mapped to 1. So the equivalence class of 1 is 1, 2, 3. So this is the equivalence class of 2, 3, 4. Now I am going to take the partition. If you take the partition which is consisting of equivalence class of 1, 4. This is the equivalence class of 1. This is the equivalence class of 1. This is the equivalence class of 4. If you take the union of equivalence class of 1 and 4, then you are going to get the given set. If you take the intersection of them, there are no common elements. Therefore, this is one partition. Similarly, this is one partition. Equivalence class of 2 and equivalence class of 4 is constituting one partition. Similarly, there is other partition. Equivalence class of 3 and equivalence class of 4 is also constituting a partition of the given set. This is how we are going to find out the partition of the given set. Next, we will see some of the gate questions which are there in the previous question papers. These questions are based on the properties of the relation, equivalence relation, and this equivalence class. The problem is this. It is given in gate 2002. The binary relation R is equal to this. This can be written like this also. R is equal to nothing means empty. They have given empty relation. Defined on the set A is equal to 1, 2, 3. They have given some empty relation defined on the set A is equal to 1, 2, 3. Now is the options are like this: neither reflexive nor symmetric, reflexive and symmetric, reflexive and transitive, symmetric and transitive. These are the options. Now look at first, they have given some empty relation. So what is the symmetric reflexive property? If for every element in this set, if there is 1, 1, 2, 2, 3, 3, then we say that that relation is reflexive relation. That relation is reflexive relation. So here the relation R is not having no ordered pairs, therefore that is not a reflexive relation. That is a irreflexive relation. So the given relation is not reflexive. The given relation is not reflexive. Not reflexive means irreflexive. Next, second one, symmetric relation. Here the relation R is empty, there are no ordered pairs. If there is A comma B, then you need to think about B comma A. So here this is not reflexive, is nothing but irreflexive. Why it is irreflexive? For all elements 1, 1, 2, 2, 3, 3 does not belong to R. That means for all elements in the set A, there is no 1, 1, there is no 2, 2, there is no 3, 3. Therefore, the given relation is irreflexive. Is it symmetric? If the relation is not having any ordered pairs, which means if there is no A comma B, then there is no need of thinking about B comma A. So here the symmetric relation says if A comma B belongs to R, then B comma A belongs to R. Then B comma A belongs to R. If A comma B belongs to R is not there, if it is false, then obviously this statement is true. So the empty relation is symmetric relation. The empty relation is symmetric relation. Next one. If there is no A comma B, if there is no A comma B and B comma C, obviously then it is transitive relation. So there is no A comma B, there is no B comma C, then there is no need of checking about A comma C. A comma C is checked when A comma B and B comma C are not there. If A comma B and B comma C ordered pairs are not there, then obviously it is transitive relation. Therefore, the answer for the given problem is symmetric and transitive. Why it is symmetric? There is no A comma B. If A comma B is there, then you need to think of B comma A. Similarly, here there is no A comma B and B comma C. If A comma B and B comma C are not there, then there is no need of thinking about A comma C. Therefore, the given relation, whatever empty relation they have given, it is symmetric relation and transitive relation. The correct option for the given problem is D. Similarly, look at next problem. So this is the problem. It was given in GATE 2009. So the relation is binary relation. They have given some binary relation. R is equal to x comma y, x comma z, z comma x, y comma z comma y. On the set A is equal to 1 comma x comma y comma z. Which of the following option is correct? Which of the following option is true? Now look at here. If you look at this, there is no x comma y. There is no y comma, there is no x comma x. There is no y comma y. There is no z comma z. That is, the given relation is irreflexive relation. So none of the option is having irreflexive relation option. Next one. Is it symmetric? Here x comma y is there, but y comma x does not belong to R. There is x comma y, but there is x comma y, but y comma x does not belong to R. Therefore, it is not symmetric. That is not symmetric. Next, is it antisymmetric? Look at here, this is like A comma B, this is like A comma B, and this is like B comma E. This is like B comma E. So in the given relation, there is A comma B belongs to R, and B comma A belongs to R, but A and B are not equal. A is not equal to B because here x comma z is there and z comma x is there, but x and z are not equal. X and z are not equal. X and z are not equal. Therefore, this is not an anti-symmetric relation. Then which option is correct? Look at R is not symmetric but anti-symmetric. But anti-symmetric. So the first option is R is symmetric but not anti-symmetric. Second one is R is not symmetric but anti-symmetric. Third one is R is both symmetric and anti-symmetric. The last one is R is neither symmetric nor anti-symmetric. The correct option is D, because whatever relation they have given, that is not a symmetric relation. Why it is not symmetric relation? X comma y is there, y comma x is not there. So with that reason, this is not a symmetric relation. Why it is not anti-symmetric? X comma z is there, z comma x is there, but both of them are not equal to each other. Therefore, the correct answer for this bit is D. R is neither symmetric relation nor transitive relation. So this is all about the today's session. In the today's session, I explained about the properties of the relation. Then I explained about the equivalence relation, and we have discussed some of the gate questions which are there in the previous question paper. Thank you for watching.